Containers are virtualization technology. You may be familiar with virtual machines. Containers follow a similar notion, but rather than simulating a machine's hardware, they virtualize an application's runtime environment, including the app's source code and its dependencies, even the operating system. Container technology has actually been around for some time and has several purveyors. One stands out from the rest, though, and that's Docker. We chose to use Docker containers for our application as it's got an impressive list of organizations that are invested in its standardization and maintenance. And when people talk about containers, usually they're talking about Docker. How Docker works and how containers work in general. On any given Unix-based operating system, the Docker engine consists of a CLI and a Docker daemon that listens for commands from the CLI and runs containerized applications. Here's an image to kind of illustrate that. These applications are encapsulated in an image. An image is a binary snapshot of an application's dependencies, be it source code, libraries, or an operating system. Images are layered objects. At an image's core will be the operating system, kernel modules that, in concert with the host operating system's core Unix-based kernel, represent the particular flavor of operating system, whether it's Red Hat Linux, Ubuntu, or Mac OS. And layered on top of the operating system image are images of other dependencies like language and framework libraries. And on top of that, your application source code. Now, all of these images are layered together and represent your application and its complete runtime environment. Any machine, physical or virtual, running the Docker engine will be able to reliably deploy your app without any concern for platform-specific configuration or limitations. And when an image is running, it's called a container. I've mentioned several times that Docker runs on Unix-based operating systems. Windows systems can host the Docker engine as well, but a virtual machine is necessary. And the idea of a virtual environment being hosted on an already virtual machine, which in turn is hosted on a physical machine, seems like an excessive amount of abstraction. However, nearly all cloud compute resources that are available today on the internet, whether it's DigitalOcean, Amazon Web Services, Microsoft's Azure, or Google's Firebase, the list goes on. But all of these are in fact virtual machines already. And spinning up a virtual machine specific to an application and its runtime environment is just as feasible an approach to application portability as containers are. However, other technologies like Docker can support several operating systems at once, while VMs are stuck with just one. And additionally, containers they just have far lower computational overhead compared to virtual machines. A containerized application can be scaled up and down at a rate that a purely virtual machine dependent application could only dream of. So in summary, why should we use containers? So in addition to scalability, which I just mentioned, containerized applications are very self-contained. A tester or a fellow developer can pull an image of an application from a repository and get straight to work without bothering with tooling up his or her workstation for application-specific technologies. Everything that they need, down to the version number, is right there in the image. Number 3, containers allow applications to be highly portable. Wherever a Docker engine is running, your app can run there too. And 4, container technology lends itself to a very modular design in your applications, and it's naturally suited for microservice oriented architectures, which are becoming more and more popular. All in all, I hope that this quick overview of container technology was informative and helpful, and I wish y'all good luck on your projects. Thanks.